depressing topic. We are looking at the divergence theorem. So good morning, everyone. I can only see one person, so that's not good. There we are. I got to see the rest of you. In particular, the divergence theorem says that if you want to find the double integral, the surface integral S of that guy, that you can find an equivalent triple integral. Oh. I think I called it R yesterday, of the divergence of F, and we'll call it dV, but dV is essentially dx, dy, dz. And what you have is a surface like this. And the boundary of the surface, right, the boundary curve might look something like this. But that guy there is the volume. That's the guy we call R. So the first kind that we did yesterday on Friday, was the simplest, and we're going to do another one of those first. And simply in those questions, you are told F, and you are given information about what the region in space that you're going to be integrating over. So the one I'm going to do right now is 2. And the vector field is x squared y plus xy squared z plus xyz squared. Is that actually one that I've done before? Because I don't think I have. Right. And the region is x goes from 0 to a, y goes from 0 to b, and z goes from 0 to c. So if you wanted to imagine what the volume that we're going to be integrating over looks like, isn't it basically a box wedged into the first octave? So that little box, right, A, B by C, is the volume that you're going to do the triple integral on. So I'm going to do, or find this guy first. And I put commas, that's that IJK, that's why I hate IJKs. There, P, comma, Q, comma, R. So the divergence is this guy, and that guy. Remember the divergence, right? If you're using operator notation, it's the grad dot product with F. So in this case, you differentiate that and you get 2xy. And if you differentiate this guy with respect to y, I think we get, can I just check something? Yep, there was a z there. This guy here gets you 2xyz, and this guy here gets you 2xyz. So you get 6xyz. That's nice. And now you should be able to put the package together. So they want us to find the surface integral. And it's going to be a triple integral of the divergence. And we'll do it as a dx, a dy, and a dz. And x's go from 0 to a. The y is going to go from 0 to b. And the z's are going to go from 0 to c. Right, if you integrate this guy with respect to x, you get 3x squared yz evaluated from 0 to a. And then once you've done that, you'll do dy, and after that you'll do dz, and the y goes from 0 to there and 0 to there. plug in A for X and plug in 0. Well, when you plug in A, you get that guy, take away nothing. Now I'll integrate this with respect to Y. And you'll add 1 to the power. And you'll divide by the new power.
Couldn't you separate them?
Darn it in space. Yes, you could. And secondly, shouldn't I have? Because isn't this a lot longer than it would be? But since I've committed to doing it the long way, I'm going to have to stick and do it that way. But you're right, I should have noticed that, and I didn't. So you're going to get the integral from 0 to C. That guy take away none. So it's going to be 3 upon 2 a squared b squared z dz. And that's going to get me 3/4 a squared b squared c squared. And if I'd separated that out, I would have got to that a lot quicker than I did. Are we okay, apart from the fact I did it the long way? So if you want to find a surface integral, convert it into the triple integral of the divergence function, evaluated. At the limits x, y, and z, whatever they happen to be. Right. Let's see what the next one has in store. Get it set up. Right. F is equal to 3xy squared, x e to the z, z cubed. That's good. And the surface is described as bounded by the cylinder y squared plus z squared equals 9, and the plane x equals -3 and x equals 3. So I need to figure out what that is going to look like in terms of what that's going to look like as a solid. So I'm going to draw the darn thing because I think it's orientated not in the usual direction. Right. So when you do y squared plus z squared equals 9, you're doing a cylinder, and the cylinder is using that plane. So basically, I'm going to have a guy that looks like this. And then that guy is going to be -3, and this guy is going to be x equals 3. So that cylinder is the solid, right? That's the region R that I'm going to be calling. Yeah, right? So we have to figure out how to set up limits of integration for a cylinder that is orientated along the x-axis instead of the usual z-axis. We're comfortable about the z-axis, right? We've done them before. Isn't that just cylindrical coordinates? So we're just going to take cylindrical coordinates and imagine that that guy, right, is that guy. So far, so good. Now, how's that going to work out? Well, normally cylindrical coordinates look like this. But wouldn't that be for cylinders going vertical on the y-axis, right? Now, using that as my basis, x is going to stay put as x. And then I can choose, I'm going to go r cos theta, and z is going to be r sin theta. Are you comfortable about cylindrical coordinates based on an axis change, right? Instead of vertical, now kind of x-axis. So make that stay put and choose these two to be your circle. So far, so good. Now, I need to find out what the limits of integration for each of these, you know, r's, x, and thetas are going to be. Well, x is easy. Doesn't it go from -3 to 3? Now, r and theta are not as bad as they seem. All I need to know is what the radius of that circle is, and I know that it's a whole circle, so I got that. And isn't the radius of the circle 3? Can you see that this is by coincidence also 3? But if that had been 16 or 25, I would have changed things. Now, since it is 3, this is also going to go 3 to -3. Are you comfortable about how we created region R?
Why is the radius -3 to 3?
And nobody knows. It's 0 to 3. Now we know. I was too busy thinking the other thing. Right, put in divergence. dp by dx, dq by dy, and dr by dz. There's your p, there's your q, and there's your r. Well, if you differentiate that with respect to x, you get 3y squared. If you differentiate that with respect to y, you get nothing at all. And this guy, you get 3z squared, which I'm now going to call 3z squared plus y squared. Now, since our integral is going to be turned into cylindrical coordinates, we have to be aware that these guys are going to have to turn into r's and thetas, right? Everybody's going to turn into r's and thetas. But here goes. The surface integral, this guy here, called the flux, is equal to triple integral. And it's going to be x goes from -3 to 3. R goes from 0 to 3. And theta goes from 0 to 2 pi. The divergence function, which is that guy, times r d x dr d theta. Made a mess of that. dx dr d theta. Okay, one little piece of the puzzle and we are good. What's y squared plus z squared equal to? And it's actually something really nice.
R squared.
You know, when it was the normal orientation, when x squared plus y squared get you r squared. But in this orientation, isn't that guy squared plus that guy squared r squared? Did I get the right one? That guy squared plus that guy squared is r squared. So we've got an r squared with one more, which is 3r cubed. And now I can throw this one open to David. David, do you think this is variable separable?
Yes.
And do you think it would be a good idea for me to do it that way?
Yep.
Okay, so I will. So it's going to be from 0 to 2 pi. I won't give that the 3. And then it's going to be r equals 0 to r equals 3. Might as well give that one the 3. And then it's going to do x equals -3 to x equals 3 of 1. Okay. This guy here gets you 2 pi. This guy at the end gets you 6. And this guy gets you 3/4 r to the 4. And 3/4 r to the 4 is 81 quarters. And that partially cancels, and that partially cancels with the other half. So I get 3 of these, I get 243 pi. And I want to see 243 pi here. Darn it. Sugar and spice. I'm 3 times 3 short. Where did I lose my 3?
You only did 3. You're supposed to do 3r to the 4th power. You did 3r.
Oh. Okay. Almost got it right. I lost an R. Question 4 is going to end up using spherical coordinates. And in particular, the shape that we're going to do it to is a sphere of radius 3. Now we have r, theta, and phi. Now at least it's an entire sphere. And if the radius is 3, we get 0 to 3. Theta is the rotation on the xy plane. So theta is going to be 0 to 2 pi. Phi is the rotation in the z-axis. So you go from here down to here. And that is 0 to pi. Are we comfortable about the spherical coordinate system on a sphere of radius 3? You comfortable with the 2 pi and the pi? Okay. Now the next bit I'm going to have to look because I've forgotten. dv is rho squared, the sine of phi, d rho, d theta, d phi. Are we comfortable with that, guy? It's just something you have to look up. Okay. Now we know what we're going to use. Let's find out what the question was. So I'll keep that at the side till I need it. In question 4, our vector field is x cubed plus y cubed plus z cubed. Oh, this is too pretty. I know where this is going to go. That guy. So I need to find the divergence. And there's our P, that's the Q, and that's the R. So it's a partial derivative with respect to X, then the middle one with Y, and the last one with Z. And you get 3x squared plus 3y squared plus 3z squared. Which if I pull out the 3, you get that guy. And we know that we're going to have to turn these into, I'm calling that R, but technically I just realized, shouldn't that be called rho? Rho, theta, phi, right? What does x squared plus y squared plus z squared get you in terms of these 3 variables? Actually, just one of them. If you turn that into this, well, I haven't written them now, but if you do the x as rho sine of theta cosine phi, I believe is the one you use for that one. But I don't need to do that. What does this give us?
Is it rho squared?
It is rho squared. So That surface integral, called the flux, is going to be the integral from phi equals 0 to pi, from theta equals 0 to 2 pi, from rho equals 0 to rho equals 3, the divergence, which is this guy, times, did I get that rho squared? Yes, times a rho squared sine phi d the other stuff. So it's going to be 0 to pi, 0 to 2 pi, 0 to 3, and I'm going to be doing a rho first. I'm going to be doing a theta second and a phi last. Would you agree this is a variable separable? So I would do from phi equals 0 to pi of the sine guy. Theta equals 0 to 2 pi, just do one of them. And rho equals 0 to rho equals 3 of that guy. Boom, 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 and off you go. Pause for a minute. Are we good? Any questions? Okay. So we've done a cylindrical one. We've done one where you needed to use spherical. And we've done ones that were just boxes, right? 0 to 1, 1 to 2, 1 to 5. Next, we're going to do a kind of ad hoc shape. So the vector field, nothing too special. E to the y tan z. And then the middle is x squared y. And then the end is e to the x cosine y. And I'm going to do the divergence first. I'll worry about the interval in a minute. There's P, there's Q, there's R. And just basically going through the mechanics, after a while, this really just becomes quite rote. With respect to X, that gets you nothing. With respect to Y, you get this guy. And with respect to Z, you get nothing. So actually, the divergence is quite simple. Put a box around that so I don't forget it. And then they told us what S is. And S is the surface that is bounded above the XY plane and below. And they describe it like this. Below the surface, Z equals 8, take away an x cubed. A -1 less than or equal to x less than or equal to 1. And a -1 less than or equal to y less than or equal to 1. And this fella has to be converted into a region in 3D. Well, 2/3 of it is done for me. All I haven't figured out yet is what the limits of integration are Z are. Now, there's not an awful lot to work with, so it's almost a case of what's in front of you has to be the answer in a lot of ways. Now, I know it's above the XY plane, and I know it's below this guy. So won't the Z be above this guy and below that guy? Are you comfortable about the Z limit of integration? So our surface integral is going to be the integral from y equals -1 to 1, from x equals -1 to 1, from z equals 0 to that horrible guy of the divergence, and then do it as a z followed by an x followed by a y. Are you comfortable about the setup? And I'm dotting on this one. There isn't really any time savers here. You can't variables, you can't separate them, right? You got to integrate them in the order. Z first, plug in these, then X's, plug in these, and off you go.
Once you integrate it with the z's, can you do a variable separable, like once it's just an integral of y and x, or?
Only if the y and x's are multiples, like if it was x squared y, you could do it. But if it was x squared plus y squared, you couldn't.
Okay, that makes sense. Thank you.
Are we comfortable about essentially how this became the limits of integration, right? That was the key. Most of the time, I don't think the divergence is going to be an issue, right? We all know how to differentiate, with the X, Y, and Z, and hopefully combine things. They're more likely to be issues when it comes to trying describing some of these weirder surfaces. So moving on to at least setting up the next one. I'll do the vector field first. It's a 6x cubed plus a single y cubed. It's a y cubed plus a z cubed. And it's a 15y squared with a z. There is nothing that I can see here that is very symmetric. So I'd be surprised if it came out nice, but I've been surprised before. So I'm just setting up the usual process for finding the divergence. If you do this guy with respect to x, you get 18x squared. If you do this guy with respect to y, you get 3y squared. And this guy with respect to z gets you 15y squared. And so we have 18x squared plus 18y squared. Interesting. Okay, well, that's the divergence right now. And they describe the surface as the solid bounded by z equals 1 take away x squared, take away y squared, and the xy plane. Okay, limits of z, 0 to that guy. Are you okay with that? XY plane, this guy. What's not so obvious is what's going to happen next. So if you find out where this guy hits the XY plane, you're really finding out when this is 0, which means that it's a circle radius 1. Are we good with that? It's a circle radius 1. which means I'm going to do these two guys. Well, technically I'm doing it cylindrical, but these two guys are polar. So I'm going to do, oops, an r from 0 to 1 and a theta from 0 to 2 pi, which kind of, there was a clue here when I saw that. What will x squared plus y squared end up looking if you use it as r's and thetas? Well, isn't that just r squared? So this fella is now 18 r squared. And so we are ready to go. Our double integral is going to be a triple integral of the divergence, which is 18 r squared. And there's going to be an r, a dz, a dr, and a d theta. The z's are going to go from, what did I do the z's? From 0 to 1 minus x squared minus y squared, which I'll fix in a minute. And then the r is going to go from 0 to 1, and the theta is going to go 0 to 2 pi. And right now, I have 18r cubed, dz, dr, d theta. Everybody has to be r, theta, or z in this combination. What will 1 take away x squared, take away y squared look like when you convert it into r and theta? Actually, just any r's. What does that guy look like?
Is it 1 minus r squared?
Are we comfortable now that that integral is doable? Right, we've got the limits integration. Right, it's going to be z first, then r, then theta. I think you probably get a variable separable after the first one. Any questions about that one before I do the last one? Okay. Final one for today, number 8. Let's do the easy bit first. Vector field, x squared z, xz cubed, y, the natural log of x plus 1, the divergence of f, differentiate with x, differentiate with y, differentiate with z. With respect to x, looks like you get 2xz here. With respect to y, don't get anything. Respect to z, don't get anything. No. Okay, there's my divergence. Okay, let's look at what this surface looks like. Well, it's just the way they're phrasing it. It's bounded by x plus 2z equals 8, y equals 6, x equals 0, y equals 0, and z equals 0. And they actually give you a little picture, which I'm just going to draw, because I don't want to have to jump out and in all the time. And essentially, your thing looks something like this. It's like a wedge. Yeah. See that? That's going to be your solid. Now, this sloping line here is the x plus 2z equals 8. And this is basically y equals, this is the y value, this is x. So x goes from, where does x go from? Well, I'll find out in a minute. If you rearrange this particular integral into z, what you get is 2z equals 8 take away x. And so z is 4 take away a half x. So I'm going to be doing from top to bottom. And from top to bottom, z is 0 on one side and 4 take away a half x on the other. Are we comfortable about how I got the limit of integration of z? I took the plane and basically the floor, right? There's your z equals 0 and there's the other guy. I used those two. So far, so good. Now, I'm going to do the y's next. 0 to 6, right? And I'm going to do the x's. 0 to somebody. Well, I know that's 0, right? What I need to know is what number there is. What is the x coordinate of that point where my finger is? Because it must be in here somewhere, hidden in this list of information. Now, when I look at most of the information that's useless, isn't this the only one that's got a fighting chance of telling me who x is? Now, what's that going to be then when you reach the xy plane? Well, when you reach the xy plane, won't z be 0? So haven't they told me x is 8? Right, so that plane, right, the sloping diagonal plane, cuts the x-axis at 8. Are you happy about the limits of integration then? The z's were from here to 0, the y's were from 0 to 6, and the z's were from 0 to where this guy hits the floor, which is at 8, x equals 8. So we put that package together. And we're going to have to do a z equals 0 to z equals 4 take away half x. And then we can do whatever order you like. I'll do x equals 0 to x equals 8. And I think y equals 0 to y equals 6. The divergence function is 2xz. You'll do a z, then an x, and then a y. And that triple integral is who you need. And it's ugly, but it's eventually doable. And I've got an answer here. Evidently, it's actually quite a nice number. It's 512. How are we doing, guys? Covered a lot today. Hopefully gave you enough, a lot of starts, a couple of finishes. Right. Telling this to all my classes, so here it goes. This coming Sunday is drop dead date for all assignments. There are no more extensions. So what you've got done by midnight Sunday is what you've got done. So it's your job to catch up with anything that you haven't managed to do. If you need an extension, you're going to have to tell me it, so I can, open it up so you can use it. Next. Maggie, when is this class's final?
Wednesday.
Okay. So we have got one more day of this, and that means that Wednesday, Thursday, and Friday is going to be a review for the final. So we'll spend a lot of time on that. I have a practice final with solutions in Canvas right now. So if you want to have a look at that, maybe give you some ideas, say asking questions on Wednesday and so on, that's great. That's about it. Last name and bye-bye. I'll hang about for questions.
Can you do like a mini variable separable with y there and say it's 6 times the integral from x to 8 times c to,
Are we talking this one here?
yeah,
I
like,
don't know yet. I'd have a look at it. So you're going to, let's see, you'd have to do this anyway. There's no way of avoiding this one. So
Yeah.
let's see what we get after we do that. So you're going to get an xz squared evaluated at 0 and at 4 take away 1/2 x. So you're going to have x 4 take away 1/2 x squared. Take away nothing. So you're going to have a dx on this guy and then a dy. You could separate it in the sense that you could do a 0 to 6
yeah, you just take a
of that
second.
guy, and then do a 0 to 8 of this horrible mess. You probably want to FOIL that out and just make it a polynomial. I don't think there's any benefit in doing any weird q-subs.
Okay, yeah.
And then times 6 essentially, because that's what that will be.
Okay, thanks.
Okay. Any questions? Any more questions?
Yeah, I was I had a question, I think, about the notation of like the formula of like the double integral of like f dot ds is equal to like the whole div thing that we just did.
Yes.
So with that, there's like the dot dv at the end, but like I guess I just wasn't sure like what that means.
So when I do a triple integral of whatever it is, right? And I do a dv like that, you're saying there's a little dot there? Is that what
Yeah,
you're
kinda
talking
like
about?
that.
That
Yeah.
little dot is just a multiplication dot. Really, you don't need it.
Okay,
When
but what is
it's a
what is-
different dot. See when you see the dot more like that. That dot is actually a dot product dot.
okay, that makes sense. But I guess like what does the dv like mean? I guess if that makes sense.
The dv is you're integrating over a volume. So a triple integral would be a dv because you're integrating over a volume.
Oh, okay, that
Right.
makes sense.
And
So
so
like
a
over
volume
surface
is
would be
really a
dv.
dx, a dy, and a dz. But a volume could also be an r, dz, dr, d theta. And technically, if you did a change of variable, couldn't you make it a du, a dv, and a dw, and then you just have to add in a Jacobian here?
Okay, yeah, that makes sense. Thank you.
Okay.